Yes, here we are. It's the physics video lecture, psci 168, video lecture 17. Okay, so I have an announcement. The last lecture had a lot of assignments in terms of going online and printing out a lot of pictures and doing a bit of research. And this one is going to be similar, so it'll also be short. I have one more really important concept in the whole business, but both of those assignments could be thought of as being due on October 2nd. So, lecture 16 and 17, homework due October 2nd, which I think is that next Friday. Yeah. Because there was quite a bit of research, or if you get into it and do it right, you're going to have to try to go up and down the Kings River and get good pictures and try to understand the whole scenario there and get pictures that show your understanding. So that can take some time, and we're going to add to that assignment today, and then you'll actually have quite a bit of material. But the hydropower concept, the way we're talking about it, is very central. In a sense, it's the centerpiece of the entire semester. After we do hydropower, we're going to switch gears and start doing thermal physics. And eventually everything's going to tie together that we're doing. But right now we're at a central part of the semester where everything that we're going to do can also be tied into this theme. So I'm going to continue with one really big cartoon for the hydropower scenario, and then try to put in as much content, and then I'll give you another continuation of last time's assignment, and we'll just see how long this takes. It shouldn't be a long lecture because I'm actually sending you out to do a lot of extra work. Okay, but I think you'll enjoy researching hydropower and researching maps and the local countryside here in the Sierra Nevada mountains, Fresno, all that. Good. So I'll just put here, we're still doing hydropower in the very general sense. And I'm actually going to use a full board to get the biggest possible cartoon here. So this is going to be a big sketch for you guys too. It's like a big half-pager, full-pager, if you do it right. Well, I have enough board up here. But I do want to bring some other elements into play. So we'll start with the usual. We've got our lake. And like I was saying, once you pursue these issues and look on Google Earth and Google Maps, I think you'll really come to a greater appreciation of all this. We've got a lake. It's held back by a dam. And if you've looked at these penstocks that I listed, you will have seen they go way down the mountain. And we understand why now. So we've got a powerhouse. And I really have to, this time, accentuate the fact that we have a lower lake down here. We have a lower body of water. It doesn't have to be that big, but it has to be there. Okay, so we have a lower body of water, and the elevation distance, the vertical distance between those water levels, that is that height difference that plays a role in our hydropower formalism. So we've got the powerhouse. We've got the penstock. We've got the dam. We've got the lake, the water. So far, so good. So the next topic that we have is called pumped storage. And part of your homework is to look this up, and there are some very nice graphics, nice images that you can get that will have all this stuff labeled and maybe with some local examples. So you definitely want to look up the pumped storage. For us, this is really key. As you know, as taking a physics class, and this is a physics class, because we still have the formula that the potential energy is just this mgh. And remember the grandfather clock, we're just lifting mass up and storing it. So pumped storage is when these hydro projects are used to store energy that's being obtained from somewhere else. We could say from out of town. So in order for that to work, we need to add these high voltage lines, and I'm going to do them out to something that we haven't talked about yet, but that we will. Okay, so we've got the high voltage lines, the powerhouse, and these are coming out of some kind of ordinary power plant, maybe a gas-fired or coal-fired power plant. Okay. So that's what this part of the cartoon is talking about. So this is a, let's just say a gas-fired power plant, or I'll put in parentheses, or coal, or nuclear, and we could even include or wind or solar. There could be some power plant outside of town, and this here is literally our, well, literally, this here we're referring to, say, Courtright Reservoir and Wishon, because they are a great pumped storage operation. Okay. So the idea with the pumped storage is this power plant is running, let's say it's in Los Angeles, okay? This thing is running and the demand is low, but you can't just shut one of these machines off like you could turn a light off, okay? So you'd rather just have it running continuously at maximum operation, and that excess energy for which there's no demand is either lost as, you know, smoke out the smokestack, or you want to store it somehow. And what's done is they send the energy to the lower powerhouse here and actually pump water up into the upper lake. They are lifting a weight from a lower place to a higher place and storing it there. So it's a very simple concept. We did the same thing with the grandfather clock. Okay. And the measurement of how much energy is there, we've already done. If you lifted a certain mass times G through a certain height difference, that's how many joules have been stored. So as simple as this sounds, it is currently the best way to store electrical energy. It's becoming more and more used because there's a whole network of dams, small ones, large ones, and especially with these so-called alternative energy sources, wind and solar, they're very intermittent, and now they're pumping water up and releasing and pumping, releasing several times a day at some of these power plants to take advantage of the sun and wind. So pumped storage is something that is becoming more important as time goes on. And it's so important to understand that the energy is coming from outside. It's being used to lift some water up there. And then it will be released and used to generate power when the demand is high. Okay, so pumped storage, look into that. That's the explanation for it. I want to add a couple of other things to our picture again, but it's becoming complete. We've got the mountains. We know we've got the water cycle. Okay. Got the water cycle. We know the water cycle is driven by solar energy. So I'll set this up here. So this cartoon here, if you fill in everything, we're going to be talking about thermal physics. So when you burn fuel, it produces heat. How do you get power out of that? We're going to be talking about that. There's our thermal power plant. We're going to be talking about electricity and magnetism, because that's how you get the power from one point to another. Okay. We've already talked about mechanical work, but electricity and magnetism takes us to an electric motor, which pumps the water up the hill. At that point, we're talking about mechanical work, and we know all about that already. In terms of the water cycle, we've got the sun coming in, and let me just label this cartoon while we're at it. So we've got incoming sun, right? That drives the water cycle. So we've got solar, that's what I was talking about down here. We've got solar driving the water cycle. We could also have some solar panels out here. In fact, that's going to be part of our picture. So here's a solar panel, right, that also converts sunlight to electricity, and it's part of the whole mix. Okay. So yeah, water cycle, solar energy. Okay. Solar energy, thermal physics for power plant of that type. So if you draw a cartoon like this, you can make it big and really put in every subject from this semester. After all, even G, we had to learn about motion, satellite orbits, free fall, etc., to really appreciate what this thing means. Okay, so now I'm going to describe what I'd like you to add to the previous assignment so that you have a really nice thorough section on hydropower. So we've got I'll reiterate this. Homework: images for pump storage. And if you look up the Helms project, that's going to be the one that we have up here in our backyard. Helms project, that's Courtright and Wishon. The images for pump storage, and a related topic is a hydropower project on the Columbia River. It's called the Grand Coulee Dam. So this is something we want to also look up. Grand Coulee Dam. That's on the Columbia River up in Washington State. That was a big Depression era project. For a time, it was the largest concrete object on Earth. I think 3 gorges in China is a lot bigger than that now. But this was a gigantic dam. And it had an interesting variation on the pumped storage concept. And that was to pump irrigation water. So I'd like you to also get some good images for the Grand Coulee project. Maybe some maps as well. So the idea, when we're all done, is that you have a good feeling for the overall type of project of hydropower. So we need, we have maps, we have Google Earth images. So your presentation of your images and all this theory, we want it to be tied together nicely in your notes. So get as much, or not too much, but get a good amount of these images to make this the centerpiece of our semester, so to speak. In terms of thematically, everything's in there, everything we've talked about and everything we're going to talk about. Here's another interesting thing where we can get images. I'm going to just write here dam architecture. Because we talked about structures, and there are different types of dams and they have different type of structure. You could get some images of that as well. And I had already said last time, Hoover Dam. Hoover Dam is a beautiful example of a lot of these things. So that's actually enough, because that'll give, it'll take some time to look these things up and organize them in your mind. The previous assignment I gave, I had a big list of things, and you were supposed to go down the Kings River from Courtright all the way down to Pine Flat. And generally when we're all together, I do a lot of discussion of how to read a map and give some examples of that. But if you go online, you can find all manner of maps. Okay? There are great resources there. So that's where I'm going to leave it for this topic. Next time, we will launch into thermal physics. And yeah, we have a lot of topics, but we've already covered quite a bit. So next, we will finish this off with thermal physics. And as we go through that, like I said, we'll be able to understand large-scale power plants of this type. And we're going to learn a lot of physics on the way. It's not that we jump to there at all, but we take it systematically. Pretty much everything there is about energy, we're going to cover this semester. Okay, good. Check the time, but I think this is going to be it. Yes, this is a short one. That's okay. So go ahead, look all these things up, organize them, and turn them in. Like the whole bundle, take a lot of good images, send them to me for October 2nd. Okay. Good. See you guys next time.